Uh, Welcome back to the next topic. Before we go to the next topic, let me just refresh what we did in the previous class. We discussed fundamental steps in digital image processing. In fact, uh, even though we may not use all the steps that I told you, for example, here there is acquisition, enhancement, restoration, color image processing, wavelets and multi-resolution processing, compression, morphological processing, segmentation, representation, and object recognition. All the process need not be applied because it all depends on what is the application for which you are using image processing. For example, if I just want to denoise a satellite image, I may be interested in only some of these blocks. I may not use most of these blocks. So, denoising comes under the heading of restoration. So probably after enhancement, after acquisition, if there is any need, I can do some simple enhancement and then probably I do restoration. If it is license plate recognition, I think some of these blocks are used. Color image processing, it depends on what is required. For example, if you are using color for maybe recognizing some objects, then I may need color image processing. So like this, you decide which are the blocks that are going to be used. And we also discussed that there is a knowledge base which is important. For example, when I am trying to do character recognition, I may have to know, or a priori I should know what is the characters that I am recognizing. That would help us in fact, getting a better accurate character recognition system. So with this, we actually moved on and we discussed about the components of an image processing system. And so whenever somebody is developing an image processing system, these are the various components that are required. Then we also looked into the image formation model. The gray level is a function of illumination and reflectance. It depends on the amount of illumination, it depends on the reflectance. These are some typical ranges. And a good example, in an average office illumination, you know that it's about 1000 lumens per meter square. So when the reflection is zero, or maybe if the reflection is say something about 0.01, then the minimum value of the okay, the range is about I min into R min. So minimum illumination is 1000, which is fixed, and reflectance is 0.01. So 1000 into 0.01 is about 10. And maximum reflection, it is almost equal to 1. So 1000 into 1 is 1000. So you will have the range from 10 to 1000, and this 10 to 1000 is actually shifted to an interval 0 to L minus 1, where 0 is black and L minus 1 is white. Okay, so this is what we learned in the previous class. Now in this class, let us try to understand the concept of image sampling and quantization. I think all of you have done sampling and quantization in your probably communication systems course, but there it is one dimensional sampling and quantization, and on the same lines we can understand two-dimensional sampling. So for that, what is given here is an image is given here, and what you should notice here is a scan line A to B. So if you understand one scan line, and the procedure is same for other scan lines. So let us understand for only one scan line. So from A to B, if I just plot the intensity levels as a 1D plot, this is how it looks. What does it mean? See, for example, at A, so you know this background is white, so the intensity value is high, as you can see. And till this edge is reached, the intensity value is almost same. There could be some changes. For example, the value may be slightly more in one point and slightly less, but it is almost same. You can see here it's almost constant. That is this region. And suddenly at this point, what is happening is the intensity value is going from white to black. That means it is decreasing. That is this transition. So there is a sudden decrease in the intensity level. Then from here onwards, if you carefully observe, the intensity is slightly increasing. So it is slightly increasing, and probably somewhere here it has reached the maximum. Then again, as you move down, it is decreasing. Then at this point, the transition from black to white. So sudden rise in the value, and then it almost remains constant. So this is a one-dimensional view of one scan line of the image. That means if I move from left to right, from A to B, this would be the intensity levels, as you can see. Now this variation, because there could be variation across this line. That means there could be small change in the values. That is why there is a variation here, as you can see. Now this is a 1D signal, and I think from here onwards, the explanation is your 1D processing or 1D sampling. So if I try to sample this data, as you all know, I should take regular intervals. So the sampling means I should take some regular intervals on the time axis, and at each of them, I just read the value. Hopefully you can see that there are some dots that are shown here. Let me just zoom this area so that it would be more clear to you. So observe here. So at this point, there is a sample here. At this point, there is another sample here. At this point, there is a third sample. So what you notice is these are the samples that I have taken. Depending on the sampling frequency, these samples may be close to each other or they may be far from each other. So these are the samples now. So this is the concept of sampling. This is one dimensional because from 1D continuous signal, I am getting a 1D discrete signal now. Okay, in discrete in time axis. Of course, here there is nothing like time, it is on the x direction. That's all. Now, the quantization means, these values, if you carefully observe here, for example, here, this height is different from this height. It is different from this height. Even here also, if you observe carefully, this is a different height and this is a different height. Now I should use some regular levels or some fixed levels, which are called the quantization levels. So as you can notice here, uh, this is one of the quantization level. This is the second level. This is the third, fourth, fifth, sixth, seventh, and eighth. So 8 levels are considered here. So whatever that lies in this range is taken as one level. So that's what is seen here. You can observe that this and this are almost close to each other. Both of them are taken at the same level. Similarly, you can observe, for example, if you go here, almost all these are the same quantization level. Okay, so it's taken here. Now here, all these are taken as one quantization level. And again, at this point, all these are taken as one quantization level, as you can observe. That means all of them will lie in the range of this quantization level, and I don't think there are any levels in this region, and these 4 or 5 samples are taking one quantization level. So I think this is the concept of your one-dimensional quantization, which you have already done in your communication systems course. So what you should notice here is I have taken a scan line and its 1D plot is shown here. And now you have explained how it can be sampled in time in the spatial domain, then how you can quantize. Okay. So what you get here is a discretized version of this particular scan line. So digitizing in the coordinates, we call it as sampling, and digitizing the amplitude, we call it as quantization. So I think this is known to you. So this is for one scan line. This is the values. So now each of this level can be represented by using some number of bits. For example, since here there are 8 levels, so I can use 3 bits to represent. That means this will be represented as say 000. The next level will be represented as 001, and the last level will be represented as 111. So if I represent the image by using 3 bits, the values could be anywhere between 000 to 111, which means the minimum gray level is 0, the maximum gray level is 7. So this is what we meant by uh, sampling an image and quantizing it. So again, if I repeat it on another scan line, I'll get another set of data. So this complete values of one row will be lying on one row of a matrix. So in fact, if you just store all these values in the form of a matrix, you will get actually a discretized image. So this image actually tells you, in fact, it's an exaggeration of what happens when I sample it. You can carefully observe here in this region, majority of the region is white. Therefore, you can see that this region is white. Now here in this region, this all these levels are averaged and you get one gray level. This region, all these levels are averaged, you get one gray level region. So this, we call this as pixelization. That means you are trying to read even each and every pixel of an image here. So this is a concept. A continuous time signal or a continuous signal is represented as a discrete signal here. Now each of them are, see here the intensity can vary from any low value to any high value, whereas here it has got a fixed range. Okay, that means if I use 3 bits for representation, I'll have 000 to 11 as a levels. So this is actually the concept of sampling and quantization. Okay, once I do that, whatever you get is stored in the form of a matrix. Okay, so for example, if I take the first row here, whatever values I get after discretizing, that means after sampling and quantization and representing this in okay, binary values, this value will be stored in the first row of your matrix. That means maybe the 0th row. Then if I take a second line here and do the same thing, I'll get the second row of the matrix, so on and so forth. So you will get, depending on how many scan lines you will have, you will get a matrix of size m cross n. M is a number of rows and n is a number of columns. This is how a sampled and quantized image is represented by using a matrix. Okay, and the matrix size will decide about the size of the image. Now an example is given here where it is actually D. This is a 3D view of the image and this is a two-dimensional view of the image. So you can observe here, D region is white, that means this, and the background here is of some gray level which is shown in this, and the background here, this small region is shown as black. Okay, so carefully observe the pixel values here. All these are zeros, so that's what you saw there, and these values, it's given as some 0.5, 50% of the maximum value, and these values are given as 1. Okay, so let me just show a MATLAB demo for you, just to read this. So I'll just go to the MATLAB. Okay, I hope the MATLAB window is visible to all of you. Is it visible?
Yes, sir.
Okay, so I'll now evaluate only this portion. I'm just reading an image, same thing. I'm converting it is actually an RGB image. So there is a command to convert RGB image to gray image. Okay, RGB to gray will convert an RGB image to gray image. And I am showing it as an image and then I'm running IM pixel info to see the values. Yeah, I think I need to change the folder is right. Yeah, so this is an image. I think the same image I have read. Now just carefully observe, I am moving the cursor and here you will get the x, y coordinate and the intensity value. This region, the value is 69. Just see, these are the values. So it is 69 and this region is 146. All these values are 146 and this region is 255. So since it is 255, this is looking like white. Since this is about 150, which is 50% of the gray distribution, so it is looking gray, and this is close to, in fact, black. It is not completely black, it is about 70. You can of course make it as 0 also. So by this you can understand that an image is just a matrix. So you can see it is a matrix of, I can also tell you what is the size. Okay, there is a command in MATLAB called WHOS, which will give you the size of the image actually. See, observe here, image is 640 cross 638. That is of the image. Me rows and 638 columns. So what you notice here is 640 cross 638 image, and some values are black, some values are gray, and some values are completely white. Okay, so I just want to, since you have already started MATLAB, what I want you to do is, uh, those who can, in fact, uh, do some simulation, I want you to generate an image which displays SIT. Okay, so SIT region should look white, and the background can be of any gray shade. I hope you have understood what is expected. You have to display SIT by using an image of this nature. Please try this. Let me just evaluate it in the next class or sometime. Okay, so this is how you can represent an image by using matrix. So an image is just a matrix from here onwards. It is a matrix of some number of rows and some number of columns. Okay. Now let me just continue with the discussions. So as I said, there are m columns and m rows and n columns, and in each of this, you will have some gray levels, and you can have L number of gray levels, and this L is decided by how many bits I am using to represent an image, and definitely m and n are to be positive integers, of course L also, and processing, storing and sampling hardware considerations, usually L will be taken as 2 to the power of k. What I mean is, you can have any number of gray levels. I can say I will use 4-bit image or 5-bit image or 6-bit image. That means I'll have 2 to the power of 6 gray levels. But usually, of course, I can even have other gray levels also. Usually, you will take power of 2 because you want to use some hardware consideration. So normally you know that there is only 8-bit processor. You don't have a 7-bit processor. You have an 8-bit processor, or you may have a 16-bit processor. You may have a 32-bit processor. Usually you will not have something like 20-bit processor or 15-bit processor, because you want to have it as a power of 2, so that you can have some hardware standards. Okay, so L is 2 to the power of k. K can be 0, k can be 1. Of course, if k is 0, you will have only 2 gray levels. 2 to the power of 0 is 1, that's sorry, 1 gray level, which is of no use. If k is 1, it will have 2 gray levels. I'll demonstrate this later. If k is 2, you will have 4 gray levels. Okay, so this 0 to L minus 1, we have already called it as the dynamic range of an image. 0 is black and L minus 1 is white. So this value range, dynamic range, is very important. Suppose if I have a very high dynamic range, then you will have all the values from 0 to L minus 1, and it will have a high contrast. Look at the right hand side image here. Okay, you can observe that there are, I'll demonstrate with a MATLAB simulation. So you can observe that this has got a high contrast compared to this image. What you notice here is, I neither have completely dark pixels in this image, nor I have completely white pixels in this image. That means your gray level values are very narrow. The range is very narrow. So with such a low dynamic range, if you have, you will definitely have what is known as a dull washed out look. Let me just show a demo. Okay, so I'll just run this. Okay, so I'm just reading the same image which I showed you here. The same image which I showed you here. I'm just reading it. Carefully observe. Again, I'll move my cursor and I want you to observe the pixel values. Okay. For example, look at this value. It is about 214. Now, if I go to the same position here, you can see the value is almost 255. Now, let me go to the head region here. You can see that the value is about 80. And if you go here, the value is about 15, 20. So what you notice here is the minimum here is about 80. The maximum here is about 200. So all the ranges are from 80 to 200. Very narrow dynamic range. Whereas here the minimum is about 15, whereas the maximum is about 255. That means you have almost all the values from 0 to 255. Okay. So, so notice, for example, it is even 10 here. So the gray level is ranging from minimum 0 to maximum 255, whereas here the minimum to maximum difference is less. That is why you can observe that this image is looking dull when compared to this. So we call the right hand side image as a high contrast image, and this we call it as a low contrast image. That means there is not much change between the minimum gray level to maximum gray level. Okay, is this clear? Any doubt so far? Can somebody respond?
Also.
Okay. See, if there are any clarifications or doubts, you should ask me. Otherwise, it becomes a one-way communication. Okay, assuming that these are simple things, hopefully you can definitely understand it. Now, I just have a question. I want one of you to answer. Okay, suppose if I have, say if I have a 10-bit image. Okay, so can somebody tell me how many gray levels will be there? What is the minimum gray level and what is the maximum gray level? It's a 10-bit image. What is the minimum gray level? What is the maximum gray level? How many gray levels will be there? Can somebody voluntarily respond or should I take names? Okay, I'll take name. Sujan D, are you there? Sujan D, if you're not answering, I'll assume that you're not there. Yeah, somebody has typed it on the chat window. I think it's Rahul. Let me just see what he has done. Okay, Rahul says 0 to 244. Rahul, if you can speak, please speak. I want you to justify how did you say 0 to 244?
Sir, actually it is 0 to 2 power 10 minus 1.
Yeah, who is this?
Sir, it's Rahul Kumar.
Okay,
Sir,
yeah.
it is 0 to 2 power 10 minus 1.
Yeah, so 2 power 10 minus 1, I don't think it is 244, correct?
Yes, yes, yes.
2 to the
It's
power of,
around 1023.
yeah, 1023. So you will have 1024 gray levels, so many gray levels, and minimum is 0, maximum is 1023, correct? Okay, fine. So let us move on. So you must know what would be the number of gray levels I am using. Usually the standard is 8-bit gray level, mostly. Of course, in medical images, sometimes they use 10-bit representation, but usually they are all 256 gray levels. That means 8 bits is used to represent the data. So let me just move on. Now, this is important requirement for you because this will tell you why actually whenever you are capturing videos or whenever you are having too many images in your document, why it takes more space. Okay, so and it is also important in terms of making some calculations. Now, the number of bits that I use to represent a digital image can be given by this equation. B is the number of bits, which is equal to M into N into K. Here M is the number of rows, N is the number of columns, and K is the number of bits used to represent the data. Number of bits. It's not gray levels, it is the number of bits. So suppose if I have a 1000 cross 1000 image, and if it is an 8-bit image, number of bits will be 1000 into 1000 into 8. That is how you calculate the number of bits. Suppose if I assume that it is a square image, that means the rows and columns are same, then it will be n square k. And usually we don't go for square image unless until we resize it. Normally, you know, the aspect ratio that we use is 4:3. So normally number of rows and columns will not be same in a real image. But for all our, in fact, probably analysis or maybe doing some processing, sometimes we decide we go for a square image. But the real image that you capture using your cell phone or any camera will not have rows and columns same. Okay. Now here there is a table. I think it's an easy table that you can understand. Where actually the table is given for square image just to make the calculation simpler. So suppose if it is a 32 cross 32 image, okay, 32 cross 32 image, and I use 1 bit for representing the gray level. 1 bit, okay. So k is equal to 1 means 2 to the power of 1 is 2 bits are, 2 bits are used to represent. So 32 cross 32 image, if I use 2 bits for representation by using this calculation, it is 32 into 32 into 2, which comes to 1024. 32 into 32 into 1. Sorry. So 32 into 32 into 1 is 1024. 32 into 32 into 2 is 2048. That means as I increase the number of bits used for representation, okay. So if I increase the number of bits used for representation, the size of the image is increasing. So that means a 32 cross 32 image with 8 bits for representation. 8 bits means 256 gray levels. It will be 32 into 32 into 8, which is 8192. Okay. Now if I, of course, 32 by 32 is a very small image. All of you know that it's a very, very small image. So if I increase the number of rows and columns, that means, for example, if I have a 1024 cross 1024 image, definitely even for a 1-bit representation, I need so many bits. Okay. So you can imagine 1024 cross 1024. If it is an 8-bit image, it needs so much of data. So it is just a simple calculation, M into N into K. So what you should notice here is, as the size of the image increases, as the number of bits used to represent the image increases, the amount of data to be stored or the number of bits used to represent such an image increases. So you can imagine this is 8192 cross 8192 and 8-bit image. So just observe the figure here, very, very large value. So I actually in the last class I had told you, let me during our offline class, I had asked you to check what is the resolution of the images that is captured by your cell phone. Now, can somebody tell me if you all have noticed it, any one of you, what is the size of the image in terms of rows and columns? Anybody who has verified? Nobody has checked it. The job is just to read your image captured by your cell phone and then display it and see what is its. Okay, if you have not done, I'll give you probably one more day, maybe on Monday, some of you can tell me. The job is just to take out your cell phone, capture an image, use MATLAB to read that image. If you use the command WHOS, it will tell you what is the size. I'll demonstrate. Yeah, I think Sumuk is answering. He says it is 1024, sorry, 4032 cross 3024. Okay. Um, Actually, it means that you will have 3024 rows and 4032 columns. That is what it means. Because normally the number of columns will be more compared to number of rows. So 3024 into 4032. So suppose if it is an 8-bit image, that means I'm assuming that it is not a color camera, it is a gray camera. Okay. So you can imagine it is 4032 into 3024 into 8 bits. Yeah, okay. So what is the size? It's a very large value. But normally your cell phone cameras are color cameras. So if it is not into 8, it is into 24. All of you know that. I use three matrices to represent. So 4032 into 3024 into 24 will be the number of bits used to represent one frame. Okay, so at least one of you have answered. Another thing I just want you to know is what is the resolution of your cell phone camera when I capture video? Usually, when you capture video, the frame size will be less. That means, the rows and columns used to represent each frame will be less. So I want you to figure it out. If you know, you can tell me now. Otherwise, in the next class, you can tell me. Okay, I hope you understood. It is not a okay, frame that you are capturing. You just capture a video. I am interested in knowing what is the uh, frame dimension. Okay, so let me just demonstrate okay, the size or the dimension. So I'll just run an image. This is a child image which I have read, and you can see that it's a color image. So what I have done here is I have read this child image and I am just showing it. And WHOS is a command to check the size of the details of this X. So if you just say WHOS and go to the command window, it would display. See, observe the size. It is 347 cross 490 cross 3. So this into 3 indicates that it is a color image. Okay. So into 3 means it is a color image. That means you are representing 347 cross 490 in 3 matrices. One matrix for red, one matrix for green, and one matrix for blue. I think those of you have started this on-ramp course on image processing. Probably the second section is to understand this concept of RGB. Okay, so 347 into 490 into 3 is the size. 3, as I said, it is for color image. That means I use 3 matrices for representation of data. And if you multiply all this is the number of bytes. Okay, this is the number of bytes. So 347 into 490 into 3. And if each of them is represented by using 8 bits, so you will actually get so many bytes. Okay. So that is the concept. Let me continue with the simulation. Now what I do is I have converted this color image into gray image, and I just want to run this command. So now it is gray image. Okay. Previously it was color image. This was a color image. So now it is gray image. And let me see what is the size now. So you can see that it is 347 into 490. That into 3 is missing because now color information is gone. It is only a gray image. Observe there is 1/3 in fact the requirement. This is so many bytes and this is so many bytes. So this into 3 will give me this. Obviously the calculation is simple. So that means what? If you process a color image, the data size will be very high. I'm talking about only one frame. Please remember this. This is for one frame. Let us do a problem which explains you how to calculate it for videos. Okay. So this is what you should understand. Number of bits used to represent any data, any image is calculated by using this simple formula. M is the number of rows, n is the number of columns, k is the number of bits used to represent the data. Usually 8-bit is used, but it can be different. Okay, so before going to this, let me just give you a simple problem. Okay, I hope you can see the problem. I'll explain what it is, but I want you to calculate and tell me the answer. So what it says is a common measure. Is this Word document visible?
Yes,
Yes,
sir.
Okay. So what it says is a common measure of transmission for digital data is the baud rate. All of you know the definition of baud rate. How many bits per second? That is the baud rate. Usually when you transmit data, it is transmitted in terms of packets. And just to have synchronization, you may add some number of start bits and stop bits. So what he says here is, he is using 8 bits for representing the data, and there is a start by a bit used and a stop bit used. So as you can see, one stop bit and one start bit for every 8-bit of data. That means every 8-bit data get added with 2 more bits, one start bit and one stop bit. Okay, so this is the principle used. Now what he wants is, how many seconds would it take to transmit a sequence of 500 images? Please understand this. A sequence of 500 images of size 1024 cross 1024 pixels with 256 intensity levels using 10 to the power of 6 bits per second baud. Okay, modem. So the modem that you are using is 10 power 6 bits per second baud modem, and normally this is one standard DSL speed. And the question continues, what would be the time to transmit the same data using 10 to the power of 9 bits per second baud modem? Okay, so what is asked is the time required to transmit the data. Now first you should calculate what is the size or what is the data size, then the number of the time that is required to transmit this data. So I will give you 5 minutes time to solve this problem, and let me just wait for your answer. Okay, 5 minutes for you. I'll specifically ask maybe some of you to answer it. If you cannot do it, we will definitely do it. Okay, so please, I have left the problem as it is. First, calculate the number of bits to represent this data. What is the data? 1024 cross 1024 image. Each pixel is represented by using 8 bits, because 256 gray levels means 8 bits I am using to represent. But you please understand, every 8-bit data gets added with 2 more bits, one start bit and one stop bit. That means even though it is 8-bit information, additional 2 bits for synchronization. So every pixel will be now 10 bits now, because every pixel should get added with a start bit and stop bit. So 10 bits totally. And it is not one image I am transmitting. I am transmitting a sequence of 500 images. A sequence of 500 images. Okay. So calculate the number of bits. Once you get the number of bits, you know the baud rate, calculate the time required. I want somebody to answer if you have already done. Okay. Tejas, yes, are you there?
Sir.
Okay. So have you started calculating? Do you have calculator nearby?
Still calculating. Sir.
Yeah, okay, do it. Okay, anybody with the answer? Vinay Kumar? I think Sindhura has given an answer. 5 nanoseconds. This is for first one or second one?
First one.
5 nanosecond. Can you just elaborate how you have done?
Sir, by taking baud rate, in 1 second, 10 power 6 bits can travel.
Okay. No,
So
no.
we
What is the
have 10
total?
bits of data.
First number of bits. What is the number of bits?
10 into 500.
10 into 500. 500 is the number of images. How many images are there? 500 images. And what is the size of each image? Yeah, some of, I think Rahul Kumar says 1.953 second. First one. I have a different answer, so let me just see whether anybody else will correct you. Shivam, are you there?
Yes, sir.
Yeah, did you calculate
Sir, doing so.
or doing it? Rahul, can you just elaborate how you have done? Rahul Kumar.
Yes, sir. Sir, actually, I got the baud rate as it will be total 2 power 10, sir, for 1024.
What is the 2 power 10?
Sir, for 1024, we will get 2 power 10 in.
For 1024?
Sir, actually, it is 8 bits, so we will add 1 bit in starting and end. So it will
Correct.
be total 10 bits.
10 bits. That is for every okay image. Okay. What is the size of the image?
It's 1024
Oh,
into
so what?
1024.
So 1024 into 1024 into 10. This would be for one image, correct?
Okay. Yes, sir.
Okay. Yeah, Sumuk, I think you are correct. Sumuk has given the answer 5200. This is for part one, 5242.88. Okay. So, yeah, we are continuing, Rahul. 1024 into 1024 into 10 into 50.
Okay, sir.
Sorry, into 500. Sorry,
Into
500
500,
into.
right?
Okay. So, what is this figure? Okay, I think I can write it. Let me just use my OneNote so that others can also copy it. Yeah, so let me just write on this. Hope my OneNote is visible to all of you.
Yes, sir.
Is OneNote visible? Okay, so we will start with the question. You have 1024 cross 1024 pixels, and you use synchronization bits. So each frame or each image, okay, for each image, the number of bits is 1024 into 1024. This is the image size into 2 plus 8. I'll write it like this just for you to understand. 8 bits for each bit, for each pixel, but I need to add one start and one stop bit. So 1024 into 1024 into 8 plus 2 is 10. Okay. So many bits for each image. But how many such images are there? So for 500 images, number of bits will be 1024 into 1024 into 10 into 500, because 500 images are to be transmitted. And this, I think it's a big number. I'll write it. I hope this is correct. 5242880000. So many bits I need to be transmitting on the baud. So time required is equal to number of bits divided by the baud rate. So in first case, the baud rate is given as 10 to the power of 6, I believe. 10 to the power of 6 bits. Okay, so 5242880000 divided by 10 to the power of 6. Okay, so this will be correct now. 5242.88 seconds. Is this correct? Any doubt, or any of you getting a different answer? So this is for, yeah, okay, this is for the first one. The second one, same thing, but now the baud rate is different. So I think this is a simple calculation. I don't think there is any. So this is, I think the baud rate is 10 to the power of 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Is it 5.242? Okay, is the problem clear? Any doubt?
Yes, sir.
Okay, yeah. So I think this is what is very important to calculate the requirement of. So you can imagine, even with a baud rate of 10 to the power of 6, to transmit 500 images means it is not too much great. I don't think that 500 images. See, normally the number of frames that I use standard is 25 frames per second. 25 frames per second. This is the video resolution that I use. So 500 divided by 25 means it is only about 20 seconds video. 500 images means I would have given you a 20-second video, that's all. because each second there will be 25 frames. So 20-second video means it is 25 into 20, which will be 500 images. So all of you know 20-second video is a very short video. I don't think anything can be noticed in a 20-second video. Now imagine if I just use okay if I just capture about 2 minutes video, okay, what would be the size? You can just observe here. Assume let me just take a different problem just for you to understand what would be the size. Okay, okay, so this is a different problem. Let us assume that I am using or I will just take the example of Sumuk's okay cell phone. Sumuk, can you just let me just see. So according to Sumuk, his cell phone is 4032 cross 3024. So 4032 cross 1024. Now since it is a color image, you need 24 bits for representation. This is because it's a color image. And let me assume that Sumuk has used this camera to capture a 2-minute video. So 2-minute video means it is 2 into 60 seconds. Okay. Now just if you just calculate this, this will be a huge number. Let me just do it for you quickly. 4032 into 3024 into 24. 24 because it's a color image. 2 into 60 because it's a 2-minute video. That is what I'm just trying to calculate. So 24 into
Sir, 25 we should
120.
multiply this.
Pardon?
Sir, we need to multiply with 25
Oh,
for
okay. Oh, sorry. There is one more term into 25. Because each second you will have 25 frames. So 25 frames per second. Yes. So let me just write the problem. 4032 cross 3024 image, color image. 2-minute video at 25 frames per second. Yes, I forgot this. So if you just do this multiplication, I think the calculator will give a very, very big number, something like 10 to the power of 11, 8.77 into 10 to the power of 11. So you can imagine 8.77 into 10 to the power of 11 bits just for 2-minute video. So this is the reason why when you capture color video and try to store it, it takes a lot of memory space on your hard disk. Okay. Is the calculation understood what we are doing? Any doubt on this? I think we are about to wind up. Any doubt? Anybody?